Hello, here we are with our last video for Chapter 8. This is the Section 4 video on effusion and diffusion of gases. As always, you'll see the learning objectives are listed here. Please pause the video and copy these in your notes. As you can see, the first objective here is to distinguish and define and explain the difference between diffusion and effusion. So let's start with diffusion, concept that we've talked about with regards to the gas laws and properties of gases is gases fill their containers completely. The kinetic molecular model told us that happens because gas particles are in constant random motion. So this idea that the process by which a gas disperses to fill that space is called diffusion. And then you can see here it's going to disperse from areas of a higher concentration to areas of lower concentration. So in this first picture, our gas molecules are packed together here. So we have a high concentration of gas molecules, but the rest of the space is empty, so low concentration of gas molecules. So diffusion means that the gas molecules will disperse into this empty space where there's a low concentration of molecules to balance that out. There is a formula for rate of diffusion. You can see the definition here. It's just how much gas is passing through some area during a period of time. So they give you this information with the amount of gas and the time frame in which they are observing the movement of that gas. Next is effusion. And so this is how a gas particle passes through a small opening or hole. So you can see kind of the difference here in these two pictures. Diffusion again fills how the gas fills that space, and then effusion is this idea of the gas particles passing through a small opening or hole. Graham's law of effusion, which is our second learning objective, gives the rate of effusion of a gas is inversely proportional to the square root of its mass of its particles. So this should make some sense to us, this relationship. The larger the gas particles, the slower they will move, the slower the effusion. All right, so harder for them to pass through that small hole and less particles that will pass through over time. This means that if I have two gases at the same temperature and pressure, their ratio of effusion rates is inversely proportional to the square of their masses. Okay, so you can see the relationship here. The rate of effusion between A and B is inversely proportional to the square root of their masses. This picture here shows a little bit about the difference here between the size of the molecules and how that affects effusion. These two balloons are filled with two different gases. The balloon on the left is filled with helium, and the balloon on the right is filled with argon. 12 hours later, a picture was taken of those same two balloons, and you can see that there's a significant difference now in the size of the balloons, and the helium balloon is significantly smaller than the argon balloon. That means that is an indication of helium's faster rate of effusion than argon because the gas molecules are much smaller. We should be comfortable with, once again, coming out of the last set of videos, if I'm have in these equations masses of gases, we should be comfortable with how we've used the ideal gas law and density and molar mass and the interconnectedness between those concepts in the past for some calculations here. Also, understand very qualitatively this relationship in which will allow us to predict the rate of effusion of gases based simply on their mass. All right, that's it for this last section of from this chapter 8 on effusion and diffusion in this section.